So today we're going to tackle a concept that is, quite literally, woven into the fabric of the world around us. We're talking everything from the deepest laws of physics all the way to the data on your credit card. We are diving into the mathematical idea of a group.
Now, that is a pretty bold statement, right? A central organizing principle? I mean, what could possibly be that fundamental? Well, it means that once you learn to see the structure of a group, you start seeing it absolutely everywhere.
Okay, to get a feel for this, how about a little puzzle? What on earth could possibly connect the frantic twists of a Rubik's Cube, the super rigid structure of a salt crystal, and the secure encryption of your online data? The answer? Well, it isn't a thing. It's a hidden mathematical structure, one that's built on the idea of symmetry. And that is the common thread. Group theory is the formal language that mathematicians use to talk about symmetry itself. And I'm not just talking about visual symmetry, like looking in a mirror, but the symmetry of actions and operations.
All right, so to make this idea of symmetry of actions a little more, concrete, we're not going to start with anything too complicated. Nope, we're going to begin with one of the simplest shapes you can imagine, a plain old square.
So a symmetry of a square is basically any move, a rotation or a flip, that leaves the square looking exactly the same as when you started. And it turns out there are precisely 8 of these moves. You can do nothing, rotate it 3 different ways, or flip it along 4 different axes. This specific collection of 8 actions has a name. Mathematicians call it the dihedral group of order 8, or just D4 for short. Now, this is the really cool part. This is where we can translate these physical moves into pure maths. So if you label the corners 1, 2, 3, and 4, doing a 90-degree rotation is the exact same thing as shuffling or permuting those labels from 1, 2, 3, 4 to 4, 1, 2, 3. Get this. Every single one of those 8 symmetries corresponds to a unique shuffle of the 4 corners. Okay, so we've got our collection of 8 actions. But what makes it a group? Well, it's not just some random list. These actions follow a really strict but elegant set of rules. You can think of these as the official rules of the game for any mathematical group. Basically, any collection of things and an operation, whether that's numbers and addition, or our symmetries and combining them, has to satisfy these 4 conditions, these axioms, to be officially called a group. So let's break them down using our square.
First up, closure. This one's simple. It just means that if you combine any 2 of your symmetries, the result you get is also one of the original 8 symmetries. For instance, rotating the square 90 degrees and then flipping it horizontally gives you the exact same result as just a single flip across one of the diagonals. You can't escape the set. You're always going to land back inside this cozy little club of 8 actions.
Second, we have associativity. Now, this one sounds a bit technical, but trust me, it's pretty straightforward. It's all about grouping. If you're combining 3 actions in a row, let's say A, then B, then C, it doesn't matter if you do A, then B first, and then apply C, or if you apply A to the result of B and C. The end result is exactly the same. The parentheses can move around, but the final position of the square doesn't change. It just guarantees things are consistent.
Third, every single group has to have an identity element. This is the neutral do-nothing action. For our square, it's the action of just leaving it alone. If you combine any other symmetry with this identity move, you just get that same symmetry right back. It's kind of like the group's home base.
And finally, the inverse element. This means that every single action in the group has a buddy action that serves as its undo button. If you rotate the square 90 degrees clockwise, the inverse is to rotate it 270 degrees clockwise, which gets you right back where you started. And for a flip, the inverse is just doing the exact same flip again.
Okay, now that we have those 4 rules under our belt, let's tackle a really common point of confusion. This actually came up in a great Reddit thread where a student was trying to connect the symmetries of a square to permutations. And it's a brilliant question because it gets right to the heart of the matter. So the user correctly noticed that, hey, if you have 4 corners, there are 4 factorial. That's 4 times 3 times 2 times 1, or 24 total ways to shuffle them around. But the square's symmetry group, D4, only has 8 of those shuffles. So they were wondering how one thing could be a subgroup of the other when the numbers seem backwards. And the confusion, it all comes down to 2 very, very similar sounding names. Okay, and here is the absolute key to unlocking this whole thing. Symmetry group is a general informal term. It's the set of symmetries for a specific object, like our square. But the symmetric group, often written as S with a little subscript 4, has a very precise formal meaning. The symmetric group S4 is the group of all 24 possible permutations of 4 items, no geometry required. The 8 symmetries of our square are just a special selection, a subgroup, of all those possible shuffles.
And this right here just lays it all out perfectly. Think of all 24 possible ways to shuffle the 4 corners as this entire circle. Well, the 8 special shuffles that also happen to preserve the square's physical shape form a little subgroup inside it, the D4 group. The other 16 shuffles? They would basically tear the square apart. They aren't symmetries at all. This shows us that the square's symmetry group, D4, is a subgroup of the much larger symmetric group, S4.
So, look, we've just used a simple square to entangle this pretty tricky idea. But why does this abstract stuff even matter? Because these exact same rules, this same structure, pops up in countless other fields, which makes group theory an unbelievably powerful tool. I mean, just look at this list. In physics, the symmetries of spacetime and special relativity form what's called a group. In chemistry, group theory helps predict the properties of molecules just based on their shape. The security of modern cryptography, it's literally built on the properties of finite groups. And in computer graphics, every single time an object rotates on your screen, that's an element of a matrix group at work. This abstract idea has very, very real consequences.
Wow. Okay, we have covered a ton of ground here, from squares all the way to space-time. So what is the single most important thing to remember from all of this?
It's really this simple. A group is just a collection of actions or moves that plays by 4 simple rules: closure, associativity, identity, and inverse. And because they follow these rules, they perfectly capture the concept of symmetry. Anytime you have a system with transformations that are closed, associative, have a neutral state, and are reversible, you've got yourself a group. And that, leaves us with one last big question to chew on. We found a formal language to describe this deep pattern of symmetry, and it completely unlocked huge areas of science. So the question is, what other fundamental patterns are out there, hiding in plain sight, just waiting for us to discover the right language to describe them?